Good morning. So let's continue our lesson on spanning sets, linear independence, and the basis of a vector space. So from the previous lesson, the first part of this section, let's remember one of the key insights. I'm not gonna go through all the details, obviously, but the key insights from the previous lesson, one of the key insights is that, as I wrote here, remember, fewer than n vectors can never span Rn. Here in the corner I meant Rn, right? The space of vectors of n components, column vectors of n components. And more than n vectors may or may not span Rn. So just very briefly, we talked about last time, right? So you take, for example, the spanning set of two vectors in R3, let's say, right? Say 1, 0, 1, and then minus 2, 1, 1. And then again, without going into all the details, if you actually describe geometrically what this represents, it's actually a plane, right? So it's not going to describe the entire vector space. So it's very easy in general to see that two vectors in R3 will not span the entire R3. Visually, you can think of these two vectors as being non-parallel. So we're going to talk actually about that, what that means in terms of a more general concept of linear independence. And then of course, even easier to visualize if you have, let's say, one vector in R2. Say you're looking at a linear combination of only one vector in R2, let's say 1 minus 1. This is, of course, a line. So that's not going to be, of course, the entire R2, the entire space of column vectors with two components. So to represent the entire vector space Rn, you're going to need at least n vectors. More than n vectors may or may not span the entire space Rn. So as you can see in the following example, if I take, for instance, the vectors 1, 0, 1, minus 2, 1, 1, the previous two I mentioned here, and then let's say minus 1, 1, 2, this will also not span R3, because if you notice carefully, let's call these guys V1, V2, V3. V3 is actually the sum of V1 plus V2. So it's a linear combination of the previous two, which means that it's in the spanning set of the first two, so it's still in the same plane. All right, so then how do we know exactly when a bunch of vectors will span the entire space? And more importantly, how many do you really need, right? This is basically what leads to the concept of linear independence. And so let's establish our main definition. So we're going to call, if we have a set of vectors v1, v2, ... vn, we call this set a linearly independent set of vectors. So this set is linearly independent. If no vector in this set can be written as a linear combination of the others. Okay, so, oh, by the way, in this case, we're assuming basically non-zero vectors, just to make it clear, because obviously that's the trivial case, right? So no vector can be written as a linear combination of the others. From a practical standpoint, in order to see whether a set of vectors is or not linearly independent, well, let me take a step back for a moment. Notice that this definition comes from the necessity of actually establishing when an additional vector really expands the spanning set. If you look at the previous examples that I wrote here, obviously this set of vectors is linearly dependent, right? Because obviously the vector v3, which is the sum of the other two, is obviously a linear combination of the other two. So when one vector is a linear combination of the others, really it doesn't bring anything new to the spanning set, because as we established last time, the spanning set of v1, v2, v3 is going to be the spanning set of v1 and v2, right? So then the linearly independent property is essentially a condition to ensure that this additional vector that you bring in actually expand the spanning set, and then hopefully you'll get to a representation of the entire vector space. Now, there is a criterion of how to actually establish linear independence, which is more useful than the basic definition. So let's formulate the criterion and explain why it works. So the criterion for linear independence, v1, v2, ... vn is linearly independent if whenever you have a linear combination of those vectors equal to 0 vector. So whenever you have this equality, then we must have then C1 equals C2 ... equals Cn equals 0. So in words, we can say that the vectors are linearly independent if any linear combination equal to 0 implies 0 coefficients. Or to put it differently, the only solution of this equation, when you set that linear combination equal to 0, is the 0 solution, because obviously 0 is always a solution, right? 0 times v1 plus 0 times v2 and so on is equal to 0. But linear independence means that that is the only solution. So whenever you set a linear combination equal to 0, the only solution for that combination is the 0 solution. So why is that actually tied up to the linear independence? Because if this is not so, if you have a non-zero solution, automatically one is a linear combination of the other. So let's illustrate briefly with an example. Let's say if you have a linear combination of 3 vectors equal to 0, and suppose C1 is not equal to 0. Which means, of course, suppose C1 is not equal to 0, C2 is not equal to 0, C3 is not equal to 0, right? That means you can write V1 as a linear combination of the other, because you can solve for it. You can move the other vectors to the left side. I mean, you need at least one of the other two to not be equal to 0, obviously, right? So minus C2 over C1 V2 minus C3 over C1 V3. So as long as you have at least one of these coefficients not equal to 0, you could always solve for one vector in terms of the other, which basically means that one is a linear combination of the other. So again, from a practical standpoint, checking linear independence means verifying that the only solution of that linear combination equal to 0 is the 0 solution. Once again, linear independence sometimes is very easy to check. So for example, if I give you the following vectors, let's say 1, 1, 1, and then let's say 1, 2, minus 1. These are clearly linearly independent. Why? Because the only way for one to be a linear combination of the other is to have one of them a scalar multiple of the other, right? And then if you talk about checking two vectors to see if they have these properties, very easy to see whether that's true or not, right? So for example, to be a constant scalar v1, it'll be c, 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 right? Or, it'll be a vector with all 3 components equal to each other. So clearly the second vector v2 doesn't satisfy that property. So obviously v2 can never be a linear, scalar multiple of the other. So therefore these are linearly independent. If you have more than 2 vectors or so, as always, you may have to analyze a system of equations. So let's, for example, check whether the vectors 1, 1, 1, 1, 2 minus 1, and then let's say, what's the other one? I will choose, let's say 1, 3, 2. Is this set of vectors linearly independent or not? So let's follow through with the definition. We're going to set up our system or linear combination equal to 0. And the answer will be yes, it's a linear combination, it's a linear independent set if the only solution is 0, 0 solution, right? Which is always a solution, but the question is if it's the only solution. So depending on the size of your matrix, you can go differently, right? If you have a square matrix, so let's actually solve the system, and then I'll talk about how you actually do it differently. So if you solve the system via the row reduction, notice that to have a single solution equal to 0, right, it means that you need to have 3 pivots for linear independence, right, in the reduced row echelon form. 1 pivot for each of the variables C1, C2, C3. So if it's a 3 by 3 matrix, basically the reduced row echelon form should be equal to the identity matrix. Now when you move on and solve the system, sometimes people actually don't write the 0 column on the right, because as you move through the row reduction, obviously the last column will not gonna change because it's just made of zeros. So when you row operations, it's not gonna affect it. So you can just basically take the original matrix formed by the vectors and just produce its row echelon form. So let's just do that. 1, 1, 1, 0. Let's subtract the row 1 from the next rows. 1 minus 1, 1, 2, and 0. 1 minus 1, negative 2, 1, and 0. Yeah, I shouldn't probably carry that 0, but that's fine for now. We're going to now multiply row 2 by 2 and add to row 3. And at this moment I can even stop because it's pretty obvious. So let's divide by 5 the last row. Clearly I'm going to have 3 pivots. So clearly C1 equals C2 equals C3 equals 0. Again, formally, if you were to continue toward the reduced row echelon form, so let's do the 0 above the last pivot, 0, 1, 0, 0. So you get, you know what you get here, right? I mean, you're gonna end up with this, and then finally, of course, I'm gonna do a little bit faster here. You can pause the video and do the row reduced echelon form yourself. But the key thing is that you end up with 3 pivots, 1 for each variable, which means that the only solution is the 0 solution, which means we have a linear independent set of vectors. So in terms of systems, remember, this is one way to go about it. I mean, like this, in terms of systems, this is the criteria basically, right? I mean, when you set it equal to 0, you need 1 pivot for each variable, and in the reduced row echelon form. All right, so in a square matrix. So let's move on to the second page for other examples. So stay tuned. All right, so another observation based on the previous example. If you have an n by n matrix, that means you're looking at n vectors in Rn. To check for linear independence, you could also do it via the determinant. So remember, in this case, if you write it in the form of a matrix form, this system is like this, right? A matrix times the, well, let's call it C bar, right? So the the column of the coefficients here equals 0 bar. If we have a unique solution of the system, then it must be the zero solution, right? Because, and when does that happen? That happens if, so this happens if A has an inverse, which happens if the determinant of A is not equal to 0, right? Because in that case, what you're going to have is the solution, I mean the column of the coefficients C1, C2, C3 can be written as that inverse of the matrix times 0, which is 0. So just for n by n matrices, or in other words, n vectors in Rn, to check for linear independence, to check for linear independence boils down to checking if the determinant is not equal to 0. So I can take the determinant of the matrix. Let's produce some zeros. So let's subtract row, again, row 1 from the other ones. 1 minus 1, 2 minus 1, 3 minus 1, negative 2, 2 minus 3, negative 1. You cross out these. 1 times minus 1 minus negative 2 times 2, which makes it minus 1 plus 4, which is 3, not equal to 0. So let's write this as a remark. N vectors in Rn are linearly independent if the matrix formed, so n vectors, let's say v1, v2, dot, 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 vn, if the matrix formed by them, right, the matrix with the columns v1, v2, vn, has the determinant not equal to 0. In general, if the determinant is not applicable, so if you don't have a square matrix, you have to go by the reduced row echelon form. So let's give another example when you don't have a square matrix when you check for independence. So let's say, again, the question is to figure out if the following set is linearly independent. Let's say 1, 2, minus 1, 3, followed by 1, 0, 1, 3, and then 1, 1, minus 1, 0, for example. And again, to check for linear independence, remember, you're looking for the system C1 plus C2 plus C3 equals 0, 0, 0, 0. So these are 3 vectors in R4 this time, right? So 3 vectors with 4 components. So again, if we're lucky to spot if they are dependent, sometimes we can tell if one is a combination of the others, right? But if it's not, then again, it's not going to be clear cut whether actually such a combination exists. It depends on the case, right? So I mean, just go by the reduced row echelon form and see if you end up with 3 pivots for the variable C1, C2, C3, in which case you're going to have a linear independent set. So we have 1, 1, 1, 2, 0, 1, negative 1, 1, negative 1, and then 3, 3, 0. Right, and then that's not mandatory, but let's just keep the right hand side as if solving for a system. So let's see, we keep the first row. What I'm gonna do next, I'm going to, let's see, what's the best way to go about it. I'm gonna add, let's see, trying to figure out what's the best way to go about it. So I think I'm gonna 0, 1. Yeah, let's just use the procedure to find the reduced row echelon form, the one that is familiar. So make zeros below the first one. So minus 2 row 1 plus row 2. That gives me 0 minus 2, negative 1 and 0. Add row 1 to row 3. We have that. Minus 3 row 1 plus the last one. Minus 3, negative 3 and 0. Then I'm going to use the third row and put it in the second position after I divide by 2, because that'll give me the second pivot right there. Then I'm going to add it to row 2 and make it a row 3 now. 0, 0, negative 1 and 0. And let's just keep the last row as it is for now. Zero, 1, 0, 0. Make the third pivot. So I already know we have an independent set. And then using the second to last row, multiply that by negative 3 and add. That makes 0 everywhere here. So notice that the solution of the system is going to be C2, 0, C3, 0, C1, C2, C3 equal to 0. Because the last row ends up being all 0. So again, the key thing is that you ended up with 3 pivots, each for each variable. And therefore, each for each of these combinations. So therefore, this is a linearly independent set. All right, so one key insight here, which you can write it as a remark, fewer than n vectors in Rn may or may not be independent. All right, so let's look at the flip side. What can we say about the independence if we have more than 2 vectors, more than n vectors in R3? So let's look at the following set in R2. Let's say 2, 1, 1, 0. Actually, let's do 1, 1. Make it less trivial. And 0, minus 1. Well, I can already tell you that these will be dependent, because you can only have at most 2 pivots in the reduced row echelon form when you form your system. So that means you're bound to have non-zero linear combinations. So again, let's illustrate briefly how that works, right? So we have our linear combination equal to 0. Come up with the reduced row echelon form, minus 2, negative 1, 2 and 0. And then finally subtract the last row from the first. Minus 1 plus 2 is 1 and 0. Okay, so notice that if I solve now for the C1 and C2, C3 is arbitrary. So that means you can always find non-zero linear combinations, right? So let's say, for example, I choose C3 equals 1. That means C equals negative 1, C2 equals 2. And we can easily verify that minus 1 times 2, 1 plus 2 times 1, 1 plus 1 times 0 minus 1 is the 0, 0 vector. So therefore, we have a linearly dependent set. All right, so finally this leads to the concept of a basis. We're going to summarize what we have so far. Basically, I'm going to say it verbally now before we move on to the second page, to the next page. So, with respect to the vector made of column vectors, the space made of column vectors, how many do you need to span the entire vector set, Rn? You need at least n of them. What happens if you have more than n vectors in Rn? Those vectors will be dependent always, because you're always short of some pivots, which means that you can always come up with non-zero linear combinations. So that means to the minimum number of vectors to span the entire vector space is precisely n. And that leads to the concept of a basis, which we'll talk about on the next page. All right, so let's summarize the key insights from the spanning sets and the linear independence properties. One more time, right? So we need at least n vectors to span Rn. We established that when we talked about spanning sets. More than n is not necessary. This is the recent insight, because they will be linearly dependent. So any additional one will not change the spanning set. So therefore, n linearly independent vectors in Rn is the smallest spanning set for Rn, which is called a basis. So in general, as a definition, a basis for a vector space is a set which is both spanning set and linearly independent. So basically, we know that in R3 we're going to need three linearly independent vectors to form a basis. So in my previous example, like the first example, we established that the vectors 1, 1, 1, 1, 2, minus 1, 1, 3, 2 form a basis to Rn. Of all possible bases, the obvious and easiest one is the standard basis. So the standard basis for R3, which can be extended, a basis for R3, sorry. So a standard basis for R3 is made of the so-called unit vectors that have 0 of all components except 1. Why this is the easiest possible basis? Because obviously it's very easy to see that it's a spanning set. Any vector ABC can be written as a linear combination of 1, 0, 0, 0. Oops, this is kind of messy here. 1, 0, 0, 0, 1, 0 plus C 0, 0, 1. And it's the right number, right? Because there's three of them, linearly independent clearly, and they span the whole thing. So the number of elements in a basis, number of vectors in a basis, it's also called the dimension of the vector space. So as we kind of know intuitively, obviously the dimension of R3 is equal to 3 and etc., right? So, how do we comprise this and check for a basis? So how do we check for a basis in Rn? Well, we know that First of all, we need to know if we have the right number. If we don't have exactly n vectors, it's not going to form a basis. What happens if we have n vectors? Well, they might be dependent. So one of them might be a linear combination of the other. So therefore, they cannot span the entire vector space. So from a practical standpoint, that means the matrix, the system that forms with the matrix made of these columns should have a unique solution, right? Or in other words, if we form a matrix with the columns given by these vectors, if the row reduced echelon form of A is the identity matrix, that means n pivots, then they form a basis. And notice that there are equivalent way of actually checking this, because to have a unique solution, it's equivalent to saying that A has an inverse. So that means the determinant of A not equal to 0. So that's another way of checking for a basis. That's usually the most straightforward way. Just do the determinant, and if it's not equal to 0, then a basis. The vector space, in general, the vector space formed by the columns of a matrix is also called the column space. So another notation here that we want to be familiar with later. If A is a matrix, call A is just basically the vector space made of columns of A. So if you have n vectors in Rn, they form a basis if the column space is equal to Rn itself. So that's why essentially checking for the determinant if it's not equal to 0 is the most straightforward way of checking for a basis. So let's do another example. Let's say I have the vectors, let's say 1, minus 1, 3, 2, 1, 0, then let's say 0, 3, minus 6. Right, so these are V1, V2, and V3. Do they form a basis of R3? Right, so the most straightforward way is to just compute the determinant. In this case, we can make another 0. Let's say, let me see how I do that. Let's make let's make 0 above the middle one there, right? I'm going to multiply the second row by -2 and add to the first row. So 3, 0, minus 6, 3, 0, minus 6. You can tell already that's going to be 0, right? So if you expand the cofactor expansion by the second column, that's going to be 1 minus 1 to the 1 plus 1, and then the determinant 3 minus 6, which is 0. So not the basis, meaning that one column is a linear combination of the other. All right, so with that being said, let's actually continue now to talk about linear independence concept when it comes to vector functions or functions in general. Okay, so let's stay tuned for the next page. All right, so the last topic is to talk about the concept of linear independence in the context of functions or vector functions. So the definition is really the same. I mean, it's similar, but with a key distinction, key additional condition. So we're going to talk about vector functions. That means just like Rn vectors, column vectors, but with entries depending on a parameter, or just functions themselves, which you can think of them as column vectors with one component. So again, we're not talking about any spanning set here, just the linear independence. So as a definition, we say that v1, v2, v1 of t, okay, so imagine these vectors now depend on a variable t, as is the case in the context of differential equations, for instance. So v1, v of t, v2 of t, vn of t are linearly independent if, whenever, this is sometimes kind of confusing in this definition, so whenever you have a linear combination equal to 0 for every t, okay, that's the key thing, okay, so if you start with a linear combination that you assume to be 0 for any t, then it implies C1 equals C2, Cn equals 0, just like before, right? But it has to hold for any t. So let me start with an example when it's not independent. So notice that if I have, let's say, e to the t plus t, let me think a little bit, t minus, let's see, t minus 1, and I'm gonna have 2e to the t. Okay, these are vectors, these are just vectors by one component. 2e to the t plus t plus 1. So these are dependent, right? Because I can take twice the first, let's see, because I have 2 minus the other. Minus t minus 1 minus quantity, the other function. It should be equal to 0. 2e to the t minus 2t minus t, t minus t 0 plus 1 minus 1. Okay, so this is a linear combination. Which is equal to 0 for any t. And yet the scalars, the coefficients, are not 0, right? So these form a linearly dependent set. Okay, so the idea is that to prove dependence, you have to show that C1, C2, C3 must be 0 if the 0 linear combination holds for any t. But the key thing is this for any t, because this allows you to actually form a system in C1 and C2, C3 when, in order to see that indeed you have only the 0 solution. So let's illustrate with a set of vector functions with two components, right? So let's say I'm checking whether the vector function 2e to the t, 2e to the t, and these are vector functions, right? So minus e to the t, 3e to the t, whether they form a linearly independent set or not. So when I take the linear combination, which I assume to be 0 for any t, just plug in a convenient value for t, right? To make the system and see if you get 0, 0. Because if you get 0, 0 for a specific value of t, that means that's the only possible solution. Because it has to hold for any t, it has to hold for a particular t. So if the only thing that holds for a particular t is 0, 0, then that must be the case. Then it's going to be 0, 0 for all the other combinations. It's going to work for all the other combinations. So for example, if I plug in 0 for t, that leads to this 2x2 system, which, since I have 2x2 matrix there, I can easily check the determinant and see that it's not equal to 0. So therefore, it'll have a unique solution, which is the 0 solution. So therefore, these are linearly independent. So when you check for linear independence of functions via systems, the idea is to form a system to solve for C1, C2, and then Cn, right? Ideally just n equations for those n unknowns, right? Because then if it's to be linearly independent, then you basically have an n by n system of equations that must have only the zero solution. So what do you have when you have, so in this case we just plugged in one variable and then one value for t, and then we had our system to solve for C1 and C2. What if you don't have enough equations? Well, just plug in extra values for t until you end up with the system that you need to solve for. So for example, let's check to see if the functions e to the t, e to the minus t, e to the 2t form a linearly independent set. So again, we're gonna form our linear combination, which we assume holds for any t. Plug in three convenient values for t, the easiest one you can find. So I'm gonna plug in 0 for t. So that gives me C1 plus C2 plus C3 equals 0. Another easy one would be 1. So that gives me EC1 plus 1 over EC2 plus E squared C3 equals 0. Another convenient one is minus 1. You gotta basically avoid as much as possible these big coefficients. Then we have 1 over EC1 plus E times C2 plus e to the negative 2, or 1 over e squared C3. Then we have our 3 by 3 matrix. Look at the matrix of the coefficients and see if we have a unique solution or not. In other words, see if the determinant is not equal to 0. I'm gonna, let's see, is it worth doing a 0? Trying to think about, let's do a 0. Yeah, we'll multiply the first row by negative e. So 1 over e minus e, e squared minus e. We multiply the other one by negative 1 over e, e minus 1 over e, 1 over e squared minus 1 over e. You don't have to go that far in the computation. Just do enough, maybe with the computer, to convince yourself that this is not equal to 0. So I'm not going to bother to simplify this, but this is going to be a non-zero determinant. So therefore, you have unique solution, which means in this context the 0 solution. Right? So that means linearly independent set of functions. So when it comes for checking linear independence of functions themselves, there is another handy tool which can be applied if these functions are differentiable multiple times. And that sometimes it's easier to check, especially if the derivatives are equal to 0. That's basically another way of forming the system. One thing to notice here, this is called the Wronskian, I'll talk about that on the next page. Another way of obtaining other equations, if you so desire, is to differentiate the entire equation. Because again, if it holds for any t, it's going to hold for the derivative as well. So for example, starting with this one, I can come up with another equation, c1 e to the t minus c2 e to the negative t plus 2c3 e to the 2t equals 0. And then you can plug in 0 for t, and then find another easy equation. So there are multiple ways to find various equations which lead to that Wronskian tool, which we'll talk about on the next page. Okay, so as I mentioned on the previous page, to check another tool, right? So to check if n functions are linearly independent, provided that they are differentiable n minus 1 times, we can proceed as follows. And again, this is useful if those derivatives are actually easy to compute. So we can form a matrix of the derivatives by rows, an n by n matrix in the following way. So this is called the so-called Wronskian matrix. Right, so the Wronskian of a set of functions f1, f2, fn. We'll have the functions themselves on the first row, the derivatives, the first derivative on the second row, culminating with the n-1 derivative on the last row. So that forms your square matrix. If this Wronskian is not equal to 0 for any t, then f1 up to fn are linearly independent. Okay, so that's very useful if the derivatives are easy to compute. So let's illustrate with an example. So let's say you have a set of functions given by t plus 1, t minus 1, and let's say t squared plus 3. So especially if you have polynomials, this works very nicely, right? So in this case, the Wronskian, again, will be with the functions themselves on the first row, the derivative of the first derivative of them, and then the second derivative of them, until you form your square matrix, right? In this case, a 3 by 3 matrix. So we're going to expand the determinant by the last row. And in this case, that's going to be t plus 1 minus quantity t minus 1. It doesn't have to be a constant, by the way, as long as it's not equal to 0 for any t. So that's going to be 4, which is not equal to 0. So therefore, these are linearly independent. The converse is not actually true. So w, if w is equal to 0, does not imply that those guys are linearly dependent. So there is a counterexample. I don't know if it's actually worthwhile to go through it. Let me think a little bit if it's worthwhile. Let me make a. I'm gonna come up with an easy example maybe. Right. So usually this is. Yeah, let's look at the counterexample just for the sake of it. So let's say these counterexamples, as in many cases, work with these piecewise defined functions. So let's say your function is t third for t greater than 0, 0 for t less than 0. So notice I make it so to be differentiable, including at 0, up until the second derivative, right? Because the first derivative will be 3t squared, still differentiable at 0. The second derivative 6t, still differentiable at 0, right? But I make the second one switched. I make it 0 to be for t greater than 0, and then t third for t less than 0. Okay, so it should be pretty obvious that these functions are actually linearly independent, because one can never be a multiple scalar of the other, right? I mean, you can never get t third 0, like yeah, I mean, like if you take, for example, let's say some scalar f1 of t, that's just gonna be c t third for t greater than 0, and then 0 for t less than 0. So this is of course not gonna be equal to f2 of t, right? I mean, because you can always find a non-zero. I mean, the only way for this to be true is for, yeah, you can never have basically one in terms of a constant multiple of the other, because the piecewise defined function is switched, right? I mean, around 0. So ct3 0, no matter what c you're going to pick, is not going to be equal as a function to the function 0 t third, right? Because obviously for t less than 0, f2 is not going to be equal to 0, right? So this can never be equal to f2. So this clearly is a set of linearly independent. This is linearly independent. Yet the Wronskian is actually equal to 0 because if you look at the okay, so the Wronskian, if you take f1, f2 on the first position, f1 prime, f2 prime in the second row, so f1, f2 prime minus f1 prime, f2. Now the first derivative is equal to what? Well, let's actually think about carefully here. f1 will be t third and 0, right? For t greater than 0, for t less than 0, which is multiplied by f2 prime, which is, what is it? It's going to be 0 for t greater than 0 and 3t squared for t less than 0. But of course, because of this, the way it's defined, this is just basically 0, right? So by the same argument, if you look at the other product, that's also 0. So this is a case in which the Wronskian is equal to 0, yet the functions are linearly independent. So the converse is not true, it's only unidirectional. The Wronskian is, if it's not equal to 0 for any t, then it implies linear independence. But again, it's just in one direction. All right, so I think that's enough for today. We're going to summarize, we're going to delve into the column space in more details for a generic matrix, and that's probably our last topic of the class. So see you next time.